All right, thank you very much. So I was suggested to talk about dark matter searches in the particle colliders and also rotation curves. So I come up with this good title. All right, so as we know, dark matter exists, and the well-studied dark matter candidate it's listed in the particle physics community is called the WIMP, the weakly interacting massive particle. What you do is you assume a particle it has a mass about 100 GeV. This is so-called the weak scale, and it carries the weak interaction or the weak scale interaction. And we like the WIMP paradigm very well. The reason is that it is very predictive, actually. So I took the slide from Jonathan Fenn. It's a very old slide. You can see that you can search for WIMPs in different ways. WIMPs can collide with quarks to produce direct detection signals. In that direction, okay? So the WIMPs can annihilate to produce standard model particles, and you can search for WIMPs in the direct detection, indirect detection experiments. And you can collide two standard model particles to produce WIMPs. So that's how you search for WIMPs at particle colliders. So here I will just give you some flavor that how do you search for WIMPs at particle colliders. So this is the annihilation process. You would expect WIMP will give you the radical density in the early universe, and you can, turn this Feynman diagram around, then you will get like two quarks. You can collide each other to produce WIMPs. But if this is the only signal you are looking for, then you wouldn't get anything because WIMPs will, even if you can produce WIMPs will escape from your detector because it only carries a weak interaction, right? So you have to add something to trigger the signal. What you usually do is you add initial state radiation. So now you are looking for signals like proton-proton collisions, and you produce visible particles through this initial state radiation. You also produce WIMPs. And you cannot measure particles here, but you can measure the visible particles. Then you use energy conservation, momentum conservation to figure out what's going on in the dark sector. So this is a typical signal. Let's say it has a large hadron collider, proton-proton to monojet or monophoton. This you attach like one photon, one jet on it, plus missing energy. That is a typical such signal. So I will just give you some idea what people have done at the LHC. So this is from Atlas collaboration. So they are looking for this particular signal, quarks to, let's say, WIMPs, and you add a mediator particle, and this is initial state radiation as a photon, right? So you are looking for this signal. And so then you have several parameters. What you do is you fix the coupling constant here, you fix the coupling constant on this end, so then you have two free parameters. One is the dark matter mass, and one is the mediator mass. So you can plot, okay, you can plot the constraints regions because LHC doesn't see the WIMP signal. So this region has been excluded. You can translate this region to the direct detection cross-section. So this is dark matter nucleon cross-section. This is dark matter mass. And this region has been excluded by the Atlas result. On this plot, you also see several direct detection bonds. Those are the crystal-based experiments, and these are the xenon-based experiments. So what you can see is that for low-mass dark matter, for low-mass WIMP, the collider can do a good job in terms of searching for the signal because they are light, so you can produce them in the particle colliders. If you go to high mass region, the direct detection experiments will do a better job because in this region, the collisions actually, so in this low mass region, because because the energy is small, then you cannot trigger the signal in direct detection experiment. But in the high energy, high mass region, that because in direct detection experiment, you have the coherent effect. So you can boost the signal, but at high energy colliders, you don't have that. So that's the reason why the limit is strong. So at this point, although we have been working on the WIMP paradigm for years, at this point, we do not have convincing signals. So I think it's a good time to think about whether we're going to go on or think about something else. And in particular about, given the fact that we see the small-scale issues, as Drew mentioned in the last talk, because the WIMP is a typical SIDM candidate, is a typical collisionless dark matter candidate. And for lambda SIDM cosmology, we see there are several issues. And we are still debating that what causes these problems. So as a particle physicist, I hope that we need a new physics. So in the rest of my talk, I'm going to focus on the rotation curves. I'm going to focus on core versus Cusp problem and also the diversity problem. So this plot shows the rotation curve data for this particular dwarf galaxies. So the stellar contribution as a gas contribution. If you add them up, you do not get the observed one. So that's the reason why you need a dark matter halo. And if you take an FW profile as predicted by the lambda SIDM cosmology, and if you take you normalize the parameters such that you can get a fit in the outer skirt, you will over-predict the total rotation curve in the inner region. So this is a very old problem. The reason is that for this profile, actually, it's in the inner region, the density becomes very cuspy, and it contains a lot of dark matter mass in the central region. The data prefers to have a quarter profile. But this is not the end of the story, because you do see galaxies which are completely consistent with lambda SIDM prediction. Okay, so this is from Oma's paper. So you see the 4 galaxies, and you see that the colored bands are from hydro simulations of lambda SIDM cosmology with some feedback model. So you can see that all these 4 galaxies are consistent with lambda SIDM. So what do you do with that? So you see cores, you see cusps. The problem is really core and the cusp problem, right? So you can make the story more interesting. So what you do is you take the galaxy, you choose a galaxy that have the same asymptotic circular velocity. So here the Vmax is defined as the maximum observed or measured velocity, right? If you look at these 4 galaxies, you see that they behave very differently in the very inner region. For this galaxy, it becomes Vmax at 2 kpc, but for this galaxy, it becomes 2 kpc around 10 kpc, right? So which means the rising is linear, so which means this galaxy has a large core. But these 2 are in the middle. But this problem was first pointed out by people at Irvine, James and Manoj, and when they and others. And then when they look at the low surface brightness galaxies, they realize that if you really want to fit the data, there's big spread in the central density, right? So that is the problem. So there's another way you can parameterize this diversity problem in this plot. So you can plot for a galaxy, you can plot the circular velocity at 2 kpc, and you can also plot the maximum circular velocity, right? So each blue point represents 1 galaxy. So this plot contains about 200 galaxies, right? So you can see the spread. So the spread here is around a factor of 4. If you go to smaller or bigger systems, the spread is about a factor of 3. So then you look at the predictions. So this is a lambda SIDM cosmology prediction. It's a median value without taking into account baryons. And if you add baryons, so this is a plot from the ego simulation. It's a weak feedback. Okay, so it makes things a little worse in the high mass region. And you also see these dashed curves or dashed dotted curves. Those are the curves to indicate how much dark matter mass you have to remove such that you can bring the SIDM curve down to the observation, to match the observation, right? So that is called diversity. So what we wanted to explain is how can you accommodate such large spread, okay? So that is the goal. So when they put out the paper, they say that it's unexpected. The diversity is unexpected. But I'm going to argue that the diversity is expected if dark matter has strong self-interactions. So what is strong self-interactions? The only assumption you make here is that you assume dark matter particles have collisions. Okay? So Drew has mentioned this cross-section. This is a cross-section normalized by the mass. This is about 1 centimeter square per gram. So this is a cross-section is close to the nuclear cross-section, like a proton-neutron and a neutron-neutron scattering cross-section. You can get this number by demanding collisions happens several times in the inner region per age of the galaxy. So when you turn on collisions, the NFW profiles become shallow if the system is dark matter dominated. And so why this is the case, it's important to look at the velocity dispersion profile Okay, so this is the NFW profile, velocity dispersion, which measures how fast the dark matter particles are moving in the halo. So it's very cold in the inner region. That's the reason why the density builds up from the hierarchical structure formation. But if you turn on self-interaction to wait long 10 gig years, you'll get a profile like this. It becomes very flat. Right? So it means those inner particles will gain kinetic energy and move to the outer skirt, larger region. So the density goes wrong and the temperature increases. And if the system has a constant dispersion, which means it has a constant temperature, which means the system in the equilibrium, right? Follows the isosomal distribution. So with this, we are motivated to introduce an analytical SIDM model. So you don't need to run simulations to look at the SIDM properties. So how do we do this? So you divide our halo into two regions. One is large region. The collisions will not happen per edge of the halo. So this is the NFW profile. In the inner region, you take this isosomal distribution, right? So you treat the system as ideal gas system, just like you can essentially use the PV equals nRT. This is your high school thermodynamics, right? So if we follow the isosomal distribution, the distribution function looks like this. The central density, the minus total gravitational potential divided by the velocity dispersion squared. And this potential contains two parts. One is from dark matter, one is from baryon. And of course, you have to relate your potential to the distribution. This is just a Poisson equation. So what you do is you just solve this equation to model the SIDM halo profile. In our region, you take NFW. This is where the cross-section gets in. So you assume the collision happens at one page of the galaxy at this point. So then what you do is you just merge these two profiles together at R1 such that they have the same mass, they have same density, right? So this is a very simple model, but actually it works pretty well. So this is a calibration you can do. The blue curve is from simulations, the dotted curve from this model. The agreement is very exact. Of course, here we do not consider baryons, but if you add baryons, you also get a very good agreement. So with this, we can analyze localization curve data for, let's say, hundreds of galaxies. Otherwise, it's impossible to do, right? For each galaxy you run simulation, it's impossible, right? So how do we get there then? Well, let's look at this plot again. Let's look at those galaxies first. Those are the galaxies below the lambda CDM prediction. Then if you take a close look of this galaxy, you will find these are the galaxies below this curve is always a dark matter dominated, most likely. It's always a low mass, low surface galaxies. So because the baryons are not important for this galaxy, then you go back to this isosomal distribution. You just replace this total potential by the dark matter potential. Then you solve this, this Poisson equation to figure out what the density is. And then you know that if baryons are not important, then the central density will be lower because of collisions, and accordingly the circular velocity will be lower, right? So this point, the lowest point is about 20 kilometers per second. Within 2 sigma, SIDM can give you about 20. Right? For CDM, even within like a 2 sigma concentration uncertainty, you still cannot get a 20. So that is for those low surface brightness galaxies. Yeah.
So this is for galaxies locally, so that redshift is 0.
Yeah, right. So then, to explain the diversity problem, you have to address those galaxies. Those are the galaxies completely consistent with the NFW lambda CDM, right? So in SIDM, if SIDM only gives you a large core, then you wouldn't explain those guys, right? But if you take a close look of these galaxies, those are the galaxies with high luminosities, which means the baryon concentration is very high. But in the presence of high baryon concentration, what you're going to do is you look at this isosomal distribution, you're going to replace this total potential by baryon. And the baryon distribution varies according to the concentration. And if you can measure it, right, you can measure it by looking at the luminosity function, the luminosity distribution, you can figure out what is the baryon distribution is. So with this, you can ask what is the how this effect changes the SIDM distribution. So the effect shows in this plot. So you take a galaxy, you fix the Vmax, you fix, let's say, the total baryon mass. But you vary the baryon concentration. This is the NFW sorry, this is NFW, this is SIDM without the baryons. And if you add replace this potential by the baryon potential, you gradually, if you increase the concentration, and the SIDM density becomes higher and higher, and the core size becomes smaller and smaller. Okay, so there's a reaction on this. So this is you have to get there because all this calculation is analytical. There's no freedom. If you fix the NFW profile, you have to you will automatically get this behavior, right? So what really happens is that the thermalization due to self-interactions will lead to high dark matter density and a smaller core due to the baryonic influence. So another way to look at this is that if you have very deep baryon potential, then more and more dark matter particle will fill into the potential, and the density becomes high. So with this, we try to test how well the SIDM can explain the diversity. So we pick up like 8 galaxies, for example, here, to show the effect. Right? So the spread at 2 kpc is a factor of 4. All of them roughly have the same Vmax. The solid curves are from SIDM fit. Right? So in our first paper, we look at like 30 galaxies. So pretty much you can fit all of them. So we found that there are several effects is important. There are several effects. So one is that the scatter in the halo mass concentration relation is important because some halos are just more dense than other halos. To fit the data, for example, these 2 halos have to be 2 sigma lower than medium. And for the galaxy over there, you have to consider high concentration halo. And the baryon distribution is very important. And those are the 2 like low luminous galaxies. But for those 2, for the galaxies over there, the baryon concentration is very high. But in addition, then self-interactions will correlate the dark matter and the baryon distributions. Right? So we can move on and to make a comparison, let's say, with the feedback model. Okay? So this is a plot from the Nihao simulation. It's with strong feedback, violent feedback. So the same 8 galaxies, okay, plot here. So the gray curves are from simulations. They are simulated galaxies. Those are the outliers 3 sigma away from their simulated galaxies. And what you can see is that because they have strong feedback, you can barely touch those 2 galaxies. As 3 sigma you can fit. But then you have the trouble actually to fit the galaxy over there. Because this is the opposite. If you consider weak feedback, there's no problem you can fit a galaxy over there, but not galaxy over here. Right? So this, but it's not surprising because if you look at the observed scatter, the factor 4, the simulation gives you still about a factor 2 scatter. But SIDM can fit all of the galaxies. So we can move on, we can consider more galaxies. Okay, so recently we have done just analysis, mainly led by Anna Kwai. She's in the audience, Manoj's student, and my student, Riverside, Tao Ren. So we consider 120 galaxies. Okay, so we do 2 independent approaches. I wanted to go to details, but so it's all the detailed fit. Probably you are not interested in it. But just look at the chi-square distribution. Right? So this is SIDM. You can pretty much fit every galaxy. This is NFW. You can fit half of them. Right? So actually, these 2 approaches, the agreement is pretty well, within about 10%. Then you can check what are the prices you have to pay to get the fit. So one is you look at what is your halo. Okay? So this is most of the fits. Almost all of the galaxies can be fitted within 2 sigma concentration mass relation. Okay? So that is good statistically, which means it's favored. And you can also, the SIDM fit can reproduce the telefacial relation, although the slope is slightly different from 4, but that's okay. That's from data. And you can also check the radial acceleration relation. So that last year, Stacy and his company kind of make a big deal of this. So if you take the same Spark data sets, if you take the fixed mass to the light ratio to be 0.5, you can see that a very tight correlation between the total observed acceleration with respect to the baryonic contribution. So with the SIDM fit, So you can also get very tight correlation. You can fit this interesting the functional form, and we check the residues. Actually, the SIDM with SIDM field, the residues are very similar to whatever they have. Okay, and so you can determine what this acceleration is. Some people say that is due to mound, but I will say this is due to structure formation of the universe, and you can get this constant from concentration mass relation. All right, so we have done some simulations to confirm or to check our analytical calculation. So we get a good agreement. So of course, those are the controlled simulations, isolated simulations. It's not cosmological. But the rough idea actually stays the same. So another kind of comment, the issue you should be worried is that the analysis we have done is all assume isoformal distribution. It's so simple, right? So whether this assumption is still valid if you take into account the feedback, because in galaxy formation the feedback does exist, right? How the feedback will change. So the Tintiator is from Gavanato's group, so they wanted to kind of falsify this analytical model. So they look at the simulations with strong supernova feedback and a black hole feedback. They want to locate the effect. So this is the result. So this NFW is shown as a dash curve. Then this is CDM if you have feedback. So because of the baryon concentration is very high, actually, due to the adiabatic contraction, the CDM profile is very steep, steeper than NFW, although their feedback scheme is strong. And SIDM is shown as a blue curve, right? And they choose a very large cross section. But then they say, well, okay, looks like collisions works because compared to CDM, apparently self-interactions are very important to get this SIDM profile. And they had some better comments on this analytical model. So then I look at their result. Then I use this analytical model to reproduce these magenta curves. Right? So completely agree with the simulation. And without the baryons, you would get a large density core. So that actually, their simulation kind of confirms the analytical model we have. Then the question you ask is why this is the case, right? Why strong feedback doesn't do anything for you? Well, the problem is that with such a large cross section, the system loop becomes equilibrium very fast, right? Once the system becomes equilibrium, then you are not able to figure out what the formation history is, right? So the SIDM distribution only sensitive to the final baryon distribution, but not the formation history. So recently, James' group and with Victor, they look at they use a fire simulation, to do like a dwarf galaxy kind of halo, and to check whether strong feedback, how the strong feedback will affect the SIDM prediction. The conclusion is that the SIDM halos is much more stable than CDM halos in the presence of strong feedback. So they say this is a phi proof. Okay, this is fine. The reason is the collisions, right? Once you have large cross sections, the collisions will lead the system to reach equilibrium. That's the reason. Okay. So then you can move on to take this analysis to other systems, as Drew mentioned. So you can concede this is an early paper. You can see the dwarf galaxy, low surface brightness, and the galaxy clusters. So we took the data from Luminous paper. So I met Drew in 2013. He was nice enough to send me his data file. So we analyzed their BCG data to look into the density profile. So what you find is that for clusters, you have to get into 0.1 to make everything work. Because although you do see cores, but the core size is pretty small. It's in the order of 10 kpc. If you have a cross-section, let's say 1 centimeter square per gram, the core size would be 100 or 200 kiloparsec, which is inconsistent. So with Drew's data, actually, we derived the strongest bound on the cluster scale. It's like 0.1, which is 1 order magnitude stronger than the typical bullet cluster limit. So Oliver did a nice simulation. Actually, also they get the same limit, like 0.1. So with this, what you can do, actually, taking into account all those observations, you can measure dark matter mass without detecting dark matter particles directly. Drew showed this plot. So if you have a dark photon model and you can, there's a closed region. In this closed region, the scattering cross-section goes like from 2 to 0.1 if you go to cluster scales. You might think, well, we haven't detected dark matter yet, right? And it's kind of crazy to think about self-interactions. But we see the familiar examples in the visible sector, like Coulomb interaction, we have nuclear interaction, we have, in plasma physics, we also have this Yukawa potential because the photon has an effective mass. So if you look at the nuclear physics data book, you look at the neutron-proton scattering cross-section, it's measured, okay, it's measured, I didn't make up. So you see this behavior. All you need to do is shift this scale a little bit down, to get SIDM right. All right, so now I come back to the colliders. So it turns out in our universe, we have natural dark matter colliders from dwarf galaxies, low velocity, higher galaxies, and galaxy clusters. So from particle physics perspective, they are particle colliders. Right? You take the data from all scales, you could measure the particle parameters. So we will summarize all the cross-sections from astrophysical observations on this table. So you might be interested to take a look. Okay, it's more interesting to work on something which is unusual. Right? That's interesting. All right, I'll just finish here. Thank you.